Okay, I want to go over how we combine enthalpy and entropy in one formula in order to determine if a reaction is spontaneous. So this is an equation called free energy change, or sometimes it's referred to as Gibbs free energy, probably named after someone with the name Gibbs. And it is represented by delta G. That is the free energy component, and the way that they relate enthalpy and entropy is with this equation delta H minus T delta S. Now, you have the superscript 0 there, which basically just means standard. So standard free energy, standard enthalpy, and standard entropy. So I just wanted to go and quickly review on what conditions for enthalpy and entropy that nature favors, indicating that a reaction would be spontaneous. So for enthalpy, an exothermic reaction is favored, which is a negative delta H. And for entropy, it wants to have more randomness. And so that's going to be a positive delta S. So that is what nature favors, a negative enthalpy and a positive entropy. So going to this table that's in the book, I'm assuming none of you guys took your books home, so you can always go to my website to download the PDFs from there. But this is on page 519, and it's a table that goes through all the possible values for H and S and what the value for delta G would be. Now, the result of free energy that would result in a spontaneous reaction is a negative delta G. So if delta G is negative, the reaction is spontaneous, it will occur naturally. If delta G is positive, it is non-spontaneous and it will not occur naturally. It can be made to occur using some sort of energy, whether it's heat or electricity or something like that. So going through this table, under what conditions would a delta G be negative, meaning that the reaction is spontaneous? So for the first one, we have a negative value of delta H, which we know is already spontaneous, and a positive value of delta S, which of course is more randomness, and that's also favored for spontaneous reaction. So if you have both enthalpy and entropy being favored for spontaneous reaction, then obviously delta G is also going to be spontaneous. So just putting it into mathematical terms, going to the equation down here, if delta H is negative, and then you're subtracting it from a positive number, so a negative number minus a positive number, that's always going to be negative. And remembering that temperature is always going to be measured in Kelvin, so there's no way that you're going to have a negative temperature. So you look at it basically in two halves. What is that? Let's do orange. So look at it in two halves. You look at T delta S as one half and delta H as another half. So if you have a negative minus a positive, then the result is always negative. Okay? Looking at the next scenario, which is delta H is negative, which is exothermic, that is favored. Actually, let me go back. I don't want to do that one yet, because I want to do the ones that are iffy last. Let's do the third one. If you have a positive, sorry. Bleh. Okay, so then if you have, I'm going to go straight to the bottom to make it the opposite case. If you have a positive enthalpy, which is endothermic, that is not favored, so that would be non-spontaneous purely through enthalpy, and you have a negative delta S, a negative entropy, which is also not favored, then delta G is never negative, and that reaction will not happen at all. So let's do pink. Going down to our equation at the bottom, if you have a positive value minus a negative value, that is always going to be positive. So for, let's just go with red. So for the, let's go 1, and that's 4. So for situation number 1, where enthalpy is negative and entropy is positive, that is always going to be spontaneous. And for situation number 4, where enthalpy is positive and entropy is negative, that is never going to be spontaneous. Now, the trick comes in with situations 2 and 3. Yeah, 2 and 3. So looking at number 2, we have a negative value, which is exothermic, that is favored. But we also have a negative value of entropy, which is not favored. So let's go down to our equation and see what happens here. So if we have a negative value here, and it's going to be minus. Now here's the trick. If delta S is negative here, then you're basically going to want this part of the equation to be as low as possible, because you want this delta H, you want that to be as high a value as possible, because that's the negative part of it. The minus and negative is positive here. So you want this to be as low as possible. So at low temperatures, to keep this part, the second half, low, then it will be negative. And that's why they say it's negative at lower temperatures. I really hope this makes sense. I want to do yellow because yellow is hard to see, I think. All right, and then for situation number 3, where you have a positive endothermic positive value for delta H, which is endothermic, that's not favored, and you have a positive value for entropy, which is more random, which is favored, then this means that this side of it you want to be as high as possible, because this is going to be your negative aspect of your formula. So you want really high temperatures here. And I hope that makes sense. That is free energy.